I'm Jason, and this is joint work with Michael Ballantyne, Sanna, Byrd, and Amin. And I'm going to tell you about how to improve the performance of a very flexible kind of synthesis technique by adding staging to relational programming. So this specifically is a technique that Byrd, Ballantyne, Rosenblatt, and Might showed off at ICFP 2017. So here we have a function, definition, and use of append, and of course they can evaluate it to its value, but they can also have holes in the call to the program, but actually have the value and produce inputs that would have caused that value to be output. And they can also put holes in any position in the program text, and with some input-output examples, ask their tool to fill in that missing part of the program text. And we should be able to put these holes at any place in the program text or examples, including several places at once, and try and fill in those missing values. And holes anywhere is an important feature of the technique that they're using. And because we can write an evaluator as just a function, then we could implement, say, a regex match evaluator as a function in this and fill in missing parts of the program text there too. So this technique, this trick, is a tower of relational interpreters, tower of interpreters with the relational programming language at the bottom. And the downside is that all of those layers of interpretive overhead slow things down. And so this paper, we make it faster by translating staging, a well-known technique from functional programming for removing interpretive overhead, to relational programming. So first I need to tell you about relational programming. We want to write relational programs as logical formula, and the execution of the program uses constraint solving plus a complete search to solve for the values of logic variables. If you're familiar with the idea of constraint logic programming, you're in the right headspace. In the paper, the relational programming language we're using is one called miniKanren. So, for instance, we should want to be able to, for a given triple of terms, inhabit the append relationship when concatenating the first two yields the third. And we want to be able to put holes anywhere in that program, and the relation should be able to query for solutions to the holes that make that true for those triples. So we should be able to answer these kinds of questions. And here, for instance, is a logical specification of append. You can see that the elements of these programs are constraints, equalities over tree structures. We have logical conjunction, disjunction, and they're all used as part of recursive formulae to define relations. Here we have a recursion with a base case and a recursive case. The base case is when the first list is empty, then the relation holds if the second and third are equal. Otherwise, in the recursive case, when the first is non-empty, we introduce some auxiliary variables. In this case, the relation holds when the third element starts with the same thing as the first element, and the rest of the first element on the rest of the second, and the rest of the third are in that relation. So what's neat about this is we're familiar with expressing the semantics of evaluation relationally. It turns out that translating a semantics like this into miniKanren syntax is really straightforward, and a bunch of miniKanren programmers have done it for some really interesting interpreters. So we should be able to, if we have an evaluator implemented as an inductively defined relation, we should be able to write queries and ask for triples of terms T1, T2, and T3, where the first two are arguments to the append function, and where the whole program evaluates the interpreter to T3. And we should be able to write that as a query and ask the solver to produce solutions. So the setting so far is we've got this miniKanren language. And in that language, we've written a relational interpreter that we can query about ways to use different programs like the append function. And I'm going to use /fun and /rel for function and relation because we've got these multiple levels going on. In fact, we can look at another way to think about defining the append relation as triples for which, when we use the append function in a relational interpreter, the two arguments produce the whole program evaluates in the interpreter to the third. So we can use the append function kind of like though we'd written append as a relation. What's new in this paper is a combination of two components. First is a stage relational programming language, multi-stage miniKanren, and the second is an interpreter written in this language that uses staging annotations. So, for instance, in this case, when we have the full text of the append function, then what we're doing is pretty analogous to staging and functional programming. We annotate some parts of the program as things we expect to have at staging time, and some parts that we expect only to have at runtime. And we should be able to specialize the interpreter with respect to the append function. But where it gets interesting is the case where we don't have the full text of the append function. In a synthesis query, this is exactly the situation, right? Where we don't have the full text of the program, that's because we're trying to synthesize part of it. And this is where staging in a relational context starts to feel a little bit different. Because we have this objective of being able to add a hole to any place in the input and still have our staging system take advantage of the known part. And this scenario gives rise to a whole bunch of challenges, including how do you fall back to runtime interpretation at the right places when you don't know in advance where the holes are going to be? How do you stage in the presence of non-determinism? How do you cope with the absence of something like higher-order functions in your language? And how do you stage a program that might be used in multiple different kinds of modes depending upon what the inputs and what the outputs are expected to be? And for the remainder of this talk, I'm going to focus on the first one, how it is we fall back to interpretation. So why or how is this a problem? Well, if you don't have the full program text at staging time, then you can't have specialized the interpreter with respect to the whole program text. So we can specialize the part that we, with respect to the part that we do have, but what do we do about the rest? Well, our solution, what fills that gap, is an evaluator that's written as a relation that we use at runtime to synthesize expressions. And to focus in, these two programs have to have the same representation of values so that values can flow back and forth across, and control passes back and forth between them. So the append relation needs to use runtime evaluation to synthesize missing pieces, and that evaluator might use the append rel at recursive calls in runtime synthesis. So zoom back out, here's our full picture. The next thing I wanted to point out is that we have two different representations of the same language semantics going on here. The staging time code specialization needs to know about the same language evaluation semantics as the runtime interpretation does. At staging time, we use annotations when detecting holes. So given the part of the append function, we, using staging, produce that append relation. But we also then remove the staging annotations, and that is the interpreter that we use at runtime to do that synthesis. And this erasure property is what makes staged programming special. So these are the specs that we want. This is what we want to achieve. Next, let me tell you a little bit about the actual language that lets us produce the behavior that we want here. In functional staging, we annotate under the assumption that some of the values are definitely available at staging time, and some are definitely only available at runtime. In the context of relational programming, instead, because we're going to assume that you could have a hole in any position in the text, our annotations are either under the expectation that some values may hopefully be available at staging time or may be unknown holes, whereas other values we definitely expect only to have available at runtime. So here's a small interpreter for a language of OR expressions. And there are two different ways that we use disjunction. Just the cases are the simple ones, the base cases of true and false, the values are T and F, or we have OR expressions. We evaluate the left-hand expression, and depending upon its value, we either already know the value or we have to do another call to the evaluator. So one of the ways that we use disjunction is for the various cases of the program text. What kind of program do we have? And another is if the first expression in the OR evaluates to true or false. Now that's not about program text, that's about runtime values. So these two different kinds of disjunction lead to two different kinds of non-determinism at staging time. So here, the green part is the part of the program that we'd hope to have at staging time, and the red part is about runtime values that we don't expect to have ahead of time. So for instance, if the computation is non-deterministic because we don't have some of the program text that we wanted, because we don't have enough to decide which branch to take, that's different than when non-determinism happens because of genuine runtime branching based on dynamic data. So instead of a hole in our program text here, we have some variables, x and y, that we want to query for at runtime. And these two different kinds of non-determinism are what lead to two different kinds of staging annotations. And this distinction doesn't come up in the functional staging context. When we encounter a logic variable in what we hope to be static program text, you want to use fallback annotations to defer that whole computation at runtime. You can't specialize on unknown code since there's no meaningful specialization to do. The point is it's a logic variable, it's a hole. We don't have that part. So in that case, the correct choice is to fall back to full relational search at runtime. Whereas when non-determinism arises because of that branching based on dynamic data, you want to explicitly stage each alternative path, generating specialized code for those branches at runtime. True runtime branching involves distinct known alternative code paths. So based upon those two different scenarios, we have two different kinds of annotations. Fallback for the case when you have non-determinism due to an unknown text, and gather when your program is non-deterministic because of non-determinism in the runtime data. So performance. We measured staging time, speed up of staged over unstaged code. If you want the details, read the paper. I deliberately made this so small that you can't see it from there. Don't try, don't hurt your eyes. If you want the breakdown, see the paper. Top line numbers are that we get an average speed up of about 26 times over 21 different benchmarks for different kinds of interpreters, theorem provers, grammar checkers, parsers, regex matchers. And one of the places where we see major improvements is that really neat situation that I mentioned at the beginning, where since eval itself is just a function, we can write an evaluator in the functional language of our relational interpreter, and then put holes in the programs to that other language, and ask our synthesizer to help fill in that missing piece. So you can right now go use this synthesis technique for your language of interest if you write the interpreter in the language of our staged eval interpreter. So go home and try it. The other thing that I wanted to tell you is that if you're doing language parametric synthesis and you're trying to do some ahead of time optimization based on a given sketch of the program, then what you fundamentally have is an interpreter specialization problem. And whereas in order to specialize to that sketch, your specializer needs to understand the semantics of the language. And if you're in that sort of situation, what you should do is you want somehow to get the code that performs these two tasks from one representation of the language semantics. In the paper, we also have the multi-stage miniKanren semantics, the description of the new language forms that we added to miniKanren, comparison with functional staging, and a link to a reusable artifact you can use to go try it out now. Thank you all very much. All right, we can take them offline then. Thank you all.